All right, so let's get started. So hi everybody, my name is Davide. I did my PhD in Italy, and my whole background was about computer vision. Today I will talk about the topic that I tackled in the last year of my PhD, which is continual learning, and part of it was developed into an internship at Qualcomm AI Research, where I am working now. And yeah, let's get started. So this is the outline that I will try to follow. So first I will introduce the continual learning problem, give some definitions, some useful definitions for you to understand what I'm talking about, and some desiderata for continual learning models. Then instead of deeply diving into what we did into our CVPR 20 paper, I wanted to make it a little bit more general and more maybe useful. So I will try to touch some related works that I highlighted into different families here. Then I will, of course, talk about what we did, and I will draw some conclusions and also some personal favorite future directions for continual learning research. So the motivation beyond continual learning. So we all like deep neural networks. So that's why we're here. They are extremely powerful, extremely proficient in different tasks, from vision to language to graphs to sequence modeling to language modeling. However, they cannot, it's really hard for them to train online. And by online, I mean that if your training data comes as a stream, as a continuous stream, the way to go is to collect data from the stream, store it somewhere, and then offline training the model. So by randomly sampling data from that gigantic pool of data, and this is referred to as offline training. So you cannot usually just take data from the stream and train it. And this is a problem because, for instance, if you train a model and then new data comes available, which is maybe slightly different from the old data that you trained on, you have to retrain from scratch, or at least fine-tune the model with this additional knowledge. But you have to retain basically the whole data set. You cannot just train on the latest part of the data set. And this is from a practical and pragmatic perspective. There's also another motivation that is more in a future direction, as more of a future direction relevance. And that is that we want to build more general AI models, because the ones that we are available now, they are very proficient in very narrow and vertical and small tasks, such as classifying an image among 10 categories or 1,000 categories, translating from one language to another language. But we want really to strive for more general models that are knowledgeable of multiple domains, and they can maybe tackle multiple tasks. So continual learning is the branch of research that tries to incorporate into an already trained model new knowledge without ruining what's already there. So without discarding what the model has already learned. This will become clear, hopefully, in a second. So continual learning has many names. It's also called lifelong learning, online learning, incremental learning. And my favorite definition is the ability of a model to learn multiple tasks sequentially. And I will get to what I mean by task. But first, I want to draw some contrast between continual learning and other transfer learning research areas. So continual learning is not multitask learning. So in multitask learning, you have a single network that has some shared layers between multiple tasks, and then some task-specific classifiers, some task-specific layers that carry you for the last mile. And the other layers are typically shared. But what's different here is that these multiple tasks are trained all together jointly at the same time. Continual learning is different from fine-tuning. So if you're familiar with fine-tuning, you have a network that is proficient in one single task, and then you don't really care about that task. You care about another task, a new task that you want to add. So you discard, for instance, the final layer. you instantiate a new one, and you take advantage of the pre-trained layers in order to fast adapt those layers to the new task. But in doing that, you discard the previous knowledge. You don't care about keeping that. Continual learning is similar in some sense, but we also want to add a new task while keeping the knowledge of the old task. So we don't want to lose the performance over the first task, and we want to be able to train as many tasks as we can without losing performance over the prior ones. And why is this difficult? So this is difficult due to a problem which is called catastrophic forgetting or catastrophic interference, which was observed in this seminal paper in 1989. And what happens is that new learning, so as you learn from the new data, right, you change the weights of your model. So assuming that you have a parametric model, such as a deep neural network, those updates on the new data, they may change the weights that are involved in representing the old knowledge. And this has a bad effect, of course, as a forgetting effect over the previous knowledge. And by catastrophic, initially this term was supposed to mean that the loss over the first task is sudden. So it doesn't, so the loss of performance doesn't happen gradually, but it's very, it's very sudden. I want to highlight that this problem is really fundamental. It's really not solvable. We can devise new tricks in order to make it, in order to make it less catastrophic, but it's really bounded to the local nature of the gradient-based optimizations that we used to train deep neural networks or parametric models in general. Because when you use, for instance, gradient descent, you have this update that you apply to each parameter of the model, and that update that you compute is very local, and it's local both in parameter space, so that gradient direction only has value in a very narrow surrounding of the parameters that you're at, and most importantly, it's also local in the data, so that update depends on the data that you used in the forward pass. And if that data is not representative of the whole problem, then basically that will be a bad update for the whole problem. I hope this makes sense. So I'm talking about tasks, and I should elaborate a bit more about what I mean. So usually in research papers, tasks take the form of classification problems. So what people typically do, they take a classification problem like MNIST, SVHN, CIFAR10, ImageNet, and they split the classes into multiple sub-classification problems. So for instance, for MNIST, it's a 10-way classification problem. And I may split it into 5 binary classification problems that are observed sequentially. And in the end, the test set will be just composed of all tasks. And so tasks are not like, I will first learn image classification, then I will learn object detection, then I will learn image segmentation. It's easier than that. But these data sets that are fairly, solved from a classification perspective, if you tackle them in a continual learning setting, they may become, depending on the setting, very, very hard to tackle. So yeah, we're not done with continual learning. There's still much to be done here. I need some more definitions before delving into related works. So the first distinction is a protocol, an experimental protocol distinction, and it's about task incremental settings versus class incremental settings. So in task incremental settings during test, this is a test distinction. So during test, I will ask what class are these images, are these examples in general, given that they belong to this specific task. So in this example, I will provide the model with digits, right? And I will tell the model also that these digits were observed in task 4. So that narrows it down for either being a 6 or a 7. It can be a 2 or a 3. So this is the easiest setting among the two, and it's equivalent of building an estimator for the conditional probability of y, which are the classes, given x, the example, and an auxiliary variable, which is the task t. On the other hand, we have class incremental settings in which I just ask which class are these examples. So I don't provide the model the knowledge about the tasks that these examples were observed during training. And this relates to estimating the probability of the class given the example x only. So this is a distinction. So class incremental settings are incredibly more difficult than task incremental settings. But this is a distinction in the experimental protocol. Usually, this mirrors also a distinction in the model. So continual learning researchers, they build their own model and can either be a multi-head model or a single head model. And typically it's not 100% correct, but typically task incremental settings are tackled with multi-head architectures, and class incremental settings are tackled with single head architectures. And what I mean is that multi-head architectures have a shared feature extractor and a separate classifier for each task. And these classifiers are only used with the auxiliary variable t. So if I am solving a task 2, I will just use the head classifier for task 2. I won't use the other ones. These are completely detached and separated. However, if I don't know which task I'm solving, all these task classifiers that are trained in the training phase, they all get in some sense concatenated to the same single classifier. And of course, obtaining a single classifier out of multiple classifiers is not as easy as it seems, because there's no calibration between different heads. And yeah, it's training this kind of architecture is much more challenging. So first, a distinction between the experimental setting and then the distinction between the architecture that we're using. I hope this is clear enough. So in the last few years, due to the renewed interest in neural networks, there have been a lot of papers about continual learning, and this is a non-comprehensive list. These are my personal favorites. However, they cluster into 5, actually into more, but yeah, to keep it simple, I narrowed down to 5 categories: model growing, replay, distillation, regularization, and parameter isolation. This is a completely my nomenclature. It's not something that, yeah, it's just for the purpose of this talk. But they all share the same goal, and the same goal is to avoid forgetting by protecting important parameters for prior tasks. So this can be achieved in many different ways, but they all aim for that. And yeah, and when you build a continual learning model, you may think of these 5 aspects that you want to have. So the first one is obvious. Your continual learning model shouldn't forget previous tasks. The second one is that it should be able to operate at fixed memory requirements and compute requirements. So if as new tasks are encountered, the memory requirements and the computation requirements should be kept at least bounded and grow sublinearly with tasks. The third one is if your model should enable forward transfer or not. So forward transfer is if I learn task 1, then I learn task 2. the knowledge that I have from task 1 will be useful for learning task 2. In that case, we have forward transfer. So knowledge acquired over previous tasks is helpful for learning future tasks. On the other hand, we have backward transfer. So if we learn task 2 and task 2 is somehow correlated to task 1, we also, as we learn task 2, may improve over task 1. This is something that most continual learning models don't have, but it's something that it's it's good to it's something that is good to have or to aim for. And the fifth one is that it shouldn't store past examples. Now this rule will be we will break this rule because if you challenge extremely challenging continual learning data sets and settings, you cannot for now get rid of storing a small amount of past examples. And this, I want to give credit to Razvan Pascanu for formalizing this desiderata in its talk at CVPR 20. All right, so I will now try to give a sense of the different families of related works. I will explain, I think, one model. I will try to keep it brief for each family. I just want you guys to understand the idea. I don't want to understand all the details. I just want to understand what each of these family is doing in a broad sense. So model growing, they increase the model capacity at each new task. Then we have parameter isolation. They compute binary masks over parameters for each task, trying to highlight which parameters are important for each task, and they will freeze those parameters in future learning. Regularization, they add a loss term as they train future tasks so that they penalize some parameters variations. Knowledge distillation, these models, they use prior, the model itself in a previous state as a teacher, and rehearsal methods, they store some old inputs to train the model. All right. So the first family is model growing. This paper is very famous by DeepMind. It's called Progressive Neural Networks. It's a very early work in continual learning. So they organize the model into columns, and each column is relevant to a task. So they apply it to a sequence of reinforcement learning tasks. So they train this model to play different Atari games, and they train it in a sequence. So we first start with the first column here on the left. And this first column we learn task 1, let's say, and this column is just a sequence of fully connected layers. So it's just a neural network. When task 1 is learned, we will freeze the parameters in this column as the new task comes by, we will instantiate a new column. So new parameters, another neural network that will learn task 2, but we also include some lateral connections. So for instance, this layer here, H2, will take as input the output of the previous layer in its column, but also the output of the previous layer in the column 1. So in this way, forward transfer is enabled. So if there is some feature extraction here that is helpful, that was trained on task 1, but it was helpful also for task 2, it would be taken advantage by this layer. And of course, this column is fixed here, so it cannot change, it cannot lose the first task, and we're just training these parameters. And then we had another column for task 3, and so on and so forth. I hope this is clear. And one problem with this is that the model grows linearly with the number of trained tasks. So if you train twice the tasks, that the model grows twice as big. And also, you need to know the task labels during test. you need to know what task are you solving in order to query the correct column. If you don't know which task you are solving, you cannot use it. You cannot perform forward propagation as it is, at least. So in terms of desiderata, this avoids forgetting. This enables forward transfer via lateral connections. This doesn't store examples. However, it doesn't have fixed memory on compute for obvious reasons. And it doesn't enable backward transfer because the weights in the past columns are fixed. So if we revisit one task, for instance, if task 4 is equal to task 1, that will be treated as a completely new task, right? All right, so yeah, this was just to mention model growing family. So I'd like to explain a little bit about knowledge distillation. So I think one of the most famous papers here is Learning Without Forgetting. It's a very it's a very seminal work about using knowledge distillation for continual learning. So the way it works is that if you look at the image here, this is a multi-head architecture. It's fairly similar to the image I use for explaining multi-head architecture. So there's a shared feature extraction here. And let's say we are learning multiple classification tasks. We learned 4 tasks. So we have 4 heads that are blue. So they are already trained, right? And we want to add a 5th task. So new data comes available for the 5th task. And what we will do is to instantiate a new head with new parameters. And as we train this head, we will prevent the responses of the other heads to change much. So new data comes available, right? So you perform a forward propagation. You actually, before starting training here, you will record for all the past classification heads, you will record the responses over the new data that you have available for training. And as you train this new head with the standard classification loss, this will compute gradients for the whole network. You also, for each past head, devise this distillation objective, which is a cross entropy between the response of the, let's say, first head after just before training on the new task, and the response of the first head now. So we want to train this such that the responses over past heads doesn't change much. I hope it makes sense. And this is done with a cross entropy objective on the new head and a distillation objective, which is still a cross entropy over the previous heads. This is the knowledge distillation approach. All right, 2 out of 5. There are other, of course, model distillation approaches. End-to-end incremental learning is one of them. iCarl is another one of them, very, very famous. But yeah, they just use the same principle, so I won't discuss them. All right, the third family is regularization approaches. And perhaps this paper here is the, I would say the most influential paper in the last few years about continual learning, at least in my opinion. So this paper started a Bayesian trend in continual learning, and I'm not very proficient in Bayesian machine learning, but Bayesian people, they look at weights not as a point in the parameter space, but as a probability distribution. So training becomes performing inference over the weights given the data set. And you want to compute during training the posterior distribution over the weights given the data set. And if you apply the Bayes rule, this resolves into having a likelihood term, which is what you usually, if you're not a Bayesian person, optimize when training a neural network, plus a prior term over the weights that is a regularization term. So you don't want your weight distribution to drift much from the prior belief that you have. And there's also an additional term that doesn't depend on the weight, so it's usually discarded. Why is that relevant for continual learning? Because this prior term here in continual learning setting becomes the posterior over the first task. So if you have two tasks, in this case A and B, you train on task A, without particular priors, and then when you train on task B, the posterior over the weights will be given by the maximum likelihood over the dataset B, plus a regularizing factor here, which is the posterior of the first round, so over task A. And this prevents the weights to drift much from the map estimate at dataset A. So this is the Bayesian view of continual learning, but this really translates into this formula here. If you assume that the distribution over weights is Gaussian, that as a diagonal covariance matrix, this translates into this objective, and this objective is formed by just train on task B, so minimize the loss over the task B, right? And also regularize the weights with this factor here. So this factor it's a summation over the weights. You have an hyperparameter controlling the strength of this loss factor, which is fixed for all weights, but each weight has a quadratic penalty. So we will penalize the change of the weight, the ith weight, with respect to its value after training on task A. And what's important is that this penalty is not constant over all the weights. It will be modulated by this Fi, and this Fi is a weight-specific number. It's a weight-specific modulation that tells you, well, this weight is very important, so changing this weight from the optimal estimate after task A will be very costly in terms of objective, and this weight will not be costly at all because it's not relevant. So how to compute that? In the EVC paper, that's the Fisher information matrix. It's a matrix that is estimated if you have with the gradient. If you have data, you do multiple forward-backward passes. You accumulate the square of the gradients, and you can compute this. There's an algorithm to compute this. It's related to the curvature of the loss function. But yeah, what's important is that each weight gets its own penalty for being changed. However, this requires to carry for each past task, so the final state, so the final parameters, and also a Fisher information matrix, which is as big as the parameters themselves. So, and on top of that, you also have the parameters that you're optimizing. So in terms of memory, this requires a lot of model checkpoints to be stored as you train multiple tasks. So there are some variations that I won't discuss. I just want to put it here in order to make this more scalable. One is online EWC, and another is progress and compress. They were all proposed they were both proposed in the same paper. And there are other Bayesian methods that were proposed. They mainly changed the way in which those penalties F are computed per parameter, but the overall framework is just the same. It's just a quadratic penalty over the change in the weights. But generally, these approaches are hard to scale to many tasks, either for memory or for performance. All right. So yeah, just bear with me. We have two more families, rehearsal-based methods and parameter isolation methods. So rehearsal-based methods, I chose GEM as a representative, and they will allow a small buffer of examples for each task to be stored. And so how should we use those examples rather than just replaying them to the network? Can we do something better? So the approach that this paper uses, so when examples are retrieved from the training stream, we want to minimize the loss over those new examples, right? But we also have the buffer that we can use to constrain the update. So what we do is to minimize over the parameters, the loss, of course, over the stream. But these constraints here, they tell basically that the update that we carry, the update to the weights that we do shouldn't increase the loss function over the memory buffer. So the loss function over the memory buffer is is constrained to decrease. So we have to change somehow the gradient that we apply to the weights so that these constraints are respected for all tasks. And under some mild assumptions, the authors can get to this constraint optimization problem. So for each, this is a constraint optimization problem that is performed for each batch of data. So you want to minimize, you want to find the gradient, the perturbed gradient G tilde, which is as close as possible to G, and G is the gradient from the stream, such that for each gradient coming from the past task, you have G tilde has a positive dot product with them. So you can think the buffer, you have multiple buffers, one for each past task. Each buffer will provide you a direction in feature space, right? And you want to compute the, you will also have another direction that comes from the stream. So where should you go with your step? You should go towards the direction which is close as possible to the one from the stream, but respecting the fact that the direction is compliant with all the ones coming from the buffer. I hope this makes sense. But if you do that, you are ensured not to lose performance over the buffer.
Question about this. How is the buffer decided? So it's probably a subset of the original data set from the previous tasks, but how is this subset calculated?
In this, there are many strategies. In this paper, they just use, I think, the last examples of each task. So they decide beforehand that for each task they will store a fixed number of examples, and the last ones will be those ones.
You know, because this is very, like, while you were talking, I thought about this. Why not take for each task, take all the data set and try to group it into different importance groups, where each group is like similar in nature and feature space, right? And then pick from each group just a representative and use this as a buffer.
There are some sophisticated ways of constructing a buffer, but so for instance, another paper which is called iCarl, there's a strategy called herding. So they will, so if you have like 1,000 examples and you want to narrow it down to 10, they have a greedy algorithm to select those, in feature space, the 10 points that in feature space would be as close as possible to the mean feature of all 1,000 points. But it's very hard generally to come up with these strategies. So they typically don't perform better than just selecting examples randomly.
Interesting.
Yeah, at least in my experience, there are some works that try to do that, but it's still an open research question. How to get examples smartly. Yeah. We have other questions from. All right. So This is a very elegant method, and however, it's very slow, and there have been proposed some alternative gradient projections that are much more efficient. And this is slow because for each batch there's a quadratic programming algorithm that tries to solve a constraint optimization problem. So as new tasks are encountered, this becomes painfully slow. There are some approximations of these models available that I won't discuss in the interest of time. I just want to mention some drawbacks. So this works. Gradient projection methods, they are usually experimented with small tasks, such as 1,000 examples per task, and they outperform simple rehearsal in those peculiar settings, but in more, when the tasks have enough data to be learned, simple rehearsal is equivalent basically to them. And typically it's hard to, they're typically quite slow to train. But something that they do, by constraining the gradient to have a positive dot product with a buffer, they enable backward transfer. They are not constraining any weights not to change if the change in the weight is beneficial to the prior tasks. So this is a very nice trait that they have.
All right. There is a question from Ina on the chat. So she's asking about slide 18.
Okay. Yes.
What if you can't find wave of G such that wave of G GK is much larger than 0? So I'm not sure exactly. Probably that thing in the box.
So I think the question is, what happens if this constraint optimization problem doesn't have a solution?
Mm-hmm. Yeah.
In that case, I don't remember correctly, but I think you won't update anything. So you will just keep the update. I have to double check it, but I think that is the case. Mm-hmm. So this is very conservative, right? So if I can't find any direction that is coherent with all the past tasks, I won't learn anything.
Yeah.
All right. And so this is the last slide for related works. This is parameter isolation methods. It's very relevant for what I will talk about in the second part, which is our work. So parameter isolation, they find binary masks for parameters, and these binary masks will highlight which parameters are important for the first task, the second task, and so on and so forth. So I picked PackNet here because it's very simple strategy, but quite effective. So let's say we have a convolutional kernel here that we train on task 1. So gray circles are weights trained on task 1. Then we can decide, all right, let's say 60% of the weights are not important for task 1, and we will just select them based on the weight magnitude, and we will prune them. So if we prune them, we will free up some space, and these white circles are pruned weights. And we will fine-tune the remaining ones on task 1 in order to adapt to the after pruning. Because if you prune something, if you prune a network, it's always better to fine-tune the remaining weights, the surviving weights. Then, after fine-tuning, we will freeze these weights, and in the empty spots, we can train for task 2, right? So the orange circles are trained on task 2, and then we can prune them and fine-tune the orange ones, and then go on until we finish the task or the free parameters. So this is a nice way to embed into the same convolutional kernel, into the same network, multiple tasks. And of course, during test, we are queried for solving a problem on task 1. We will take the mask of task 1, and we'll just apply this mask here. yeah, there are alternatives, piggyback and hut. I put it here, but they follow the same reasoning. And also our model that I will explain is kind of similar. So the drawback here is, again, they can only be applied in task incremental setting, because you know to you have to know how to isolate the mask during test, because if you don't know the task, you don't know which weights you should apply. And they are very intransigent. They will prioritize. So those weights are frozen. So you can basically run out as you learn new tasks of free parameters, and learning will stop basically. And yeah, there's a small memory overhead, because we have to keep binary masks during test. All right, so I hope that the 5 families were a bit clear. I will now try to explain our take on the problem, which is this paper, which was published in CVPR last year. And if you, yeah, let's get to it. Yeah. So I will start by analyzing the title. So the title is Conditional Channel Gated Networks for Task-Aware Continual Learning. There are quite some keywords here. So channel gated means that we will gate the network channels. So we will have a binary decision over network channels. Some of them will be on, some of them will be off. And conditional means that the gating is dependent on the input example. So 2 different examples will trigger different decisions for this gating. And task aware means that the model doesn't need task labels during test. So it can act in a class incremental setting. And in terms of taxonomy, our model is at the intersection between parameter isolation models, so the PackNet that I just showed you, and rehearsal models. So if we tackle task incremental settings, so if we know the task label at test time, we just need parameter isolation. We don't need any buffer. However, if we tackle class incremental setting, we will also allow during training to store some examples. And the motivation behind our work is that we like parameter isolation models. However, they cannot be applied in class incremental settings. So we were trying to, build parameter isolation models able to act in a class incremental setting. This is the main motivation. I will discuss other ones. So let's revisit a little bit the math. So this is task incremental learning, right? So we want to maximize over the parameters the log probability of the class Y given the image X and task T, right? And this is an expectation with respect to the data set of task T, the Tth task. And this is also an expectation with all the tasks that we observed. So on average, between all the tasks and all the images of that task. On the other hand, we have class incremental learning, which is the same, but we don't have T to the right side of the conditioning. So what we thought is, what if we jointly predict, given X, the class and the task? So if you do that, you can decompose this probability distribution into the good old task incremental learning. So probability of Y given XT plus something that is similar to class incremental learning here, only that we are predicting the task rather than the class. So this objective is twofold. On the one hand, we have task incremental learning of class labels. This will be regularized against forgetting with parameter isolation. On the other hand, we have class incremental learning of task labels. And this is a bit confusing, but because it's called class incremental learning, but we will have a single head over the task labels. I will explain it later. And this is regularized with rehearsal. But the important thing is that given an input, we will try to, in the end, we will try to predict both the class and the task. All right, so this is the core of our model. So let's say we have a convolutional layer, this one here. This receives an input feature map. So before applying a convolution, we will query a gating module. And this gating module is specific for each layer and each task. So at task 1, we have just one. At task 2, we will have 2 gating modules, and so on and so forth. So these gating modules decides out of the convolutional kernels that are available in the convolution, which ones should be applied to the input feature map, right? How does it perform this binary decision? So the gating module is itself a very shallow neural network with a very small overhead. The input feature map gets pooled, and then a multi-layer perceptron provides the score for each convolutional kernel. We sample binary decisions with something called Gamble softmax trick, which is a reparametrization trick for discrete distributions. It's just, I won't get into details, but it's just something with which you can train binary or more generally discrete decisions inside a neural network. So something that is not continuous. In this case, we have on-off decisions. They come out of a threshold. The threshold doesn't have a gradient, a well-defined gradient. So there's this trick in order to compute the gradients or an estimate of the gradients.
Is there a good place to read about this, a Wikipedia or somewhere else?
Gamble softmax. There are, yeah, it's becoming quite popular. I have a few references, so I will provide you them. It's like, yeah, yeah. But the way it works is that you have your logits. Usually you will do the sigmoid to get a binary decision, a sigmoid and a threshold, and you sum a vector of noise that comes from a very specific distribution, which is the Gamble distribution, and then you sample out of this, this accumulated vector, and in the backward pass you just discard the fact that you use the threshold. It's called this, yeah. But I have some references about it.
Thank you.
So on this vector, we will apply a sparsity objective. So we will ask this gating module to be very selective into the selection of filters. So we want to select during training as few filters as possible. And this gradient, it's just gets just back propagated throughout the network. And this sparsity objective will be an L1 objective. So meaning that really it asks the gating module, despite, regardless of the input, it asks the gating module just to turn off gates. So if we don't do anything else, those gates will just be turned off, right? But on the other hand, we have a classification objective that comes from the end of the network that will send gradient to the gating model itself. So this classification objective will ask the gating module to keep firing for the important parameters for that task, right? So the sparsity objective tries to turn them off, and the classification objective tries to turn them on. And as a result, only the relevant ones will be turned on. So you can, this is the sparsity objective, is just an L1 normalized by the number of filters. And as the training goes, you can see that, let me just show it once again. Here is the probability of firing for a specific convolutional kernel. The gates get, the kernels get sparsified. So we have 100 kernels available. At the end of the training of a task, we see that some of them are on 100% of the time for each test, for each example. Some of them, actually most of them, are blue, so they are completely off, they never fire. And some of them fire conditionally. So for instance, for 60% of the data, or for 10% of the data, this kind of patterns. So now we have a sense of which kernels are important for this task, right? So we can just select some filters based on a threshold of this histogram. and we use just a zero threshold. So if one kernel only fires 1% of the time, we will select it anyway, but other choices are can be made here, maybe even smarter. And those kernels will be frozen for future tasks. So future tasks, they will have their own gating modules, and these gating modules can select these yellow kernels, but cannot update them. So if some particular kernel is useful, it can be used. We can fire for that kernel, but it's not updatable, right? So this is this is a continual learning model, and we can experiment with it. So if we know which task are we solving during test, we can query the correct gating module and get the important kernels for that task. So remember that we have for each layer one gating module for each task. So we want to know which one we want to apply, right? And in task incremental setting, we have that knowledge, and we experimented in these three data sets with two different backbones. One is just a 3-layer CNN. The other backbone is ResNet 18. And we outperformed strategies such as EVC Online, which is an online version of it's a regularization-based approach. Learning without forgetting is a knowledge distillation approach, and HAT is just another parameter isolation approach. And yeah, I mean, this is a good safety check, but it performs very similarly to HAT. But given the fact that we have input-dependent firing patterns, this allows to save a lot of computation during tests. This is a nice byproduct of the fact that our gates fire conditionally on the input data, right? Because, for instance, let me see, if one task is classifying between different breeds of dogs, and very early in the network, we can understand that this example is very likely to be a golden retriever, right? The gating modules will tend to fire more kernels towards that decision, and will turn off some other kernels for other breeds of dogs, let's say. So to understand if the dog, let's say it's a Labrador or some other breed. So this is the advantage of having conditional computation based on the input. As you grow, as you keep forwarding layer by layer, fewer and fewer kernels will be active, because most of the alternatives will be ruled off. I hope this makes sense. So
I have, if it's okay to ask a question, I actually have two. If we go back to the slide with the graph, this one, yeah, with the yellow graph on the right side, with that histogram of activations. Yeah, this one. So it might be because I'm not entirely understanding, but first, did you have an expectation that you will see a constant, let's say, constant kernels that are always appearing and constant kernels that are not appearing for the entire data set across a task? Or is it something you found out after you were running your experiments?
I think it's something that you can expect. I mean, this is just conditional computation. There are many papers that do conditional computation and instantiate different inference graphs depending on the input. And if you do channel gating, which is what we do, there are these three types of kernels. So kernels that are always used, kernels that are never used if you sparsify them, and kernels that just fire conditionally depending on the. So I think this is something that we expected. Yes.
And another question: how did you check, and if you checked to see that this probability of firing is not something that is random to the data set, but that is something that is inherent in the data set according to a specific task? let's say, I hope my question was clear.
Yeah, can you please
Yeah.
repeat it?
So if you have a data set, you might, from the randomness of the data set that you have, you might find a specific probability distribution over what kernels are firing and what not. But if you have a different data set, but from the same task, maybe that probability distribution will be different, or maybe no. So now the question is, were you able to check this? And if yes, how were you able to check?
So you're asking how do we know that this specific set of kernel will generalize to the test set, let's say, will be yeah, because this is we don't, we just assume it, we never check that, but it's a good concern, I think. But yeah, we never experimented with that, but it turned out to work, at least for our data sets. But it's a good question. Thank you.
Do you hear me now?
Sorry?
Do you hear me? Because
yeah.
I could. So I had just 20. Can you go to 28th slide, please? Yeah. So what is overhead? Because you have overhead for new parameter estimation for estimating binary decision. So how many parameters do you have? I understand that you have sparsity regularization that still controls the capacity of the network, but still, so how many parameters are there?
I don't know the exact number. I think so, but compared to the convolution, it's irrelevant because what we do, we pull the input feature map, so this becomes just a vector. There's no spatial, with just one by one spatial locations, and let's say this is 64 channels, right? What we do is that we have an MLP with just one hidden layer. So we will project these 64 channels into 16 channels, and then project back to the output channels of the convolution. So there's a bottleneck even here. And overall, the parameters count, I mean, we can count them, but it will turn out to be much smaller. And also in the MAC counts, so the number of operations involved here are negligible as compared to the convolution. But I don't know the exact number.
And the second question that is somehow is related to what Peter asked. So you have gates for each of the tasks. So can you just, based on the correlation between this gated or binary decision mask, tell something about correlation between tasks themselves? Is it okay? Like.
Yeah, I guess you could ask based on the firing pattern of gates. You can devise a metric about that tells you how much task 1 and task 2 are correlated.
Or mutual dependent. I don't know how to say it.
Yeah, I guess you can do that, but we've never done that. And also, one comment: these binary patterns are local to each layer in the network, right? So I don't think that by concatenating all of them throughout the network you get a good measure about that, but you may very locally for just one layer understand that, yeah, there's a lot of feature reuse between task 1 and task 2, and so potentially they are more correlated than task 2 and task 3. But we haven't looked into that, except for one image I will show in the last slide. That's a little bit in this direction, but yeah, I think it's a good suggestion.
And as well as what Peter taught, that if data is no unimodal, but it's multimodal, it can also depend on on the bench of data, something like this one. not only correlation between the tasks, but correlation between tasks given some data sets. It's for, I don't know, it's like...
Yeah, I mean, but that's a fundamental problem that goes beyond the fact that we're selecting kernels, right? So if you have a shift between the training data set and the testing data set, you have a much bigger problem than continual learning, I would say. So yeah, it is assumed as in most machine learning models, I would say, that the distribution between training and testing is the same.
Okay, thank you.
So we're already in the 1 hour mark, actually. So I will ask also myself no comments and questions until the video you finish. And if we have more time, then we will.
Yeah. Do you want me to speed up or maybe skip some?
It depends on you, because some people, even if they don't have time now, they watch on the recording. So you can take your time. It's really more dependent on you and how much time you can give us today.
Yeah, I guess I can go to the end then without problems. Yeah.
Okay.
So yeah, we were here, and so I presented. These are task incremental results. So this is the easy setting. We don't. Yeah, we're doing good in this setting, but this is not the core that we were trying to solve. So how to? We have a lot of in our model. We have a lot of task dependent modules. So gating modules. We have one for each task, and also at the end of the network we have multiple heads. One for each task. So how can we do class incremental setting? So we will try to predict, given the input, the task label, and then use it to select the. But there is a problem, because that task label is very hard, at least in our experience, to guess from the early layers. So we spent quite some months trying to do that, to do local decisions for each task, for each layer. But in the end, what we figured out it worked better is to have a global decision at the end of the network. And I will explain this in a bit. So this is, I think, the most, a bit difficult concept or slide to explain. So just bear with me. So let's say we have a neural network made of many layers. And each layer, as I explained, has several ways of gating the input activations. And each gating module is relevant to some task, right? So we don't know what the task is. So what we do, and this may seem surprising, is that we carry on all the alternatives. So each layer will take from the previous layer a set of candidate feature maps for all the tasks. It will gate them with the relevant gating module, and will forward to the next layer a set of gated feature maps. And this carries on to the end of the network, in which we have a final set of candidate feature map and a classifier and a task classifier. So this seems obscenely wasteful, because we are doing a lot of operations. However, we measure the number of operations, the theoretic number of operations, the MAC counts. And given the fact that we are gating, actually the number of operations is much, it's quite surprising, but it's much lower than the number of operations in the backbone network itself, if we were not gating the activation. So at least for a limited number of tasks, this strategy is cheaper than performing forward propagation in the network itself. And this was quite a good surprise.
That's very elegant.
Yeah, I mean, we were, and the reason for that, we were trying to do this decision locally. So here I have a candidate set of gates, and I will commit to one decision and say, well, I think I'm forwarding task 2. But that strategy, we were never able to make it work. And in the end, we just end up to have a final classifier. So this final task classifier takes all the feature maps, it pools them, it concatenates them, and with a two further layers, it decides which task are we solving. And in this case, the decision is task 2, so it will take this blue feature map and it will forward it to the second head to get the class prediction, right? And the model here is multi-head in the classes because each classification head is separate, but it's single head in the task classifier. So now we have quite some things happening here. So just a recap. The parameters in the model are protected by gating. So we won't update the relevant parameters for the prior tasks here. These gating modules are trained separately, so they are protected against forgetting, so they cannot forget. These class head classifiers, again, they are trained separately for each task, so they won't forget. What will forget is the task classifier here, because this task classifier has some parameters and there's nothing protecting it from just drifting and just saying, all right, it's the last task, for each example. So that's why we have to introduce episodic memory here. Actually, we have to introduce memory, and we tried two alternatives. So episodic memory means the one that I explained before. We store real examples from each task into a buffer. There's another strategy that I didn't mention because it's not that popular, but it's having a generative memory. And as you may guess, it's instead of storing real examples, we will store fake examples from a generative model like again, a VAE, normalizing flows, or your generative model of choice. And in our case, we use the Wasserstein GAN for that. So if we compare, so the top plots are for episodic memory, and we outperform other replay-based methods such as AGEM and iCar. These are quite popular. AGEM I also mentioned in this talk. And we can see that for different buffer sizes on both datasets, we can do better. Surprisingly, we weren't able to train AGEM on MNIST. These are very poor performances, but on SPHN, which is a more difficult data set, it performs quite good, I would say. But we never found out the reason for that. And when it comes to generative memory, so we have one GAN that we train alongside our model, and at the end, we will just fire a lot of fake examples to store, and then discard the generator and instantiate a new one for the new task. So it's quite, it's quite complicated. We are adding modules and modules, but I'm finished. I won't add other neural networks during training here. So we compare with DGM, which is a very nice paper from Ostapenko and others from CVPR 19. And we were able to also in a more difficult data sets like ImageNet 50, quite remarkably outperform the existing the best performing model. Now this is a 50 class classification problem, so this accuracy is still very low. So there's still much improvement to be gained here. I don't want by any means to claim that our model solves ImageNet 50, but it's a good improvement. And there are some remarkable gaps also for other data sets. So, all right. So this kind of works. I have some a couple more slides about. So the first one, I particularly like this one because episodic memory models for continual learning and generative memory models for continual learning, they kind of compare against each other, but they never. it's not clear which strategy between episodic memory or generative memory should be used for a continual learning problem. So what we did is to compare them by considering the memory consumption. So we can compute, we can plot the memory consumption against the accuracy, and by memory consumption for the episodic memory, we refer to the size of the stored examples without compression, and for the generative memories, the bytes needed to store the generator, basically, that what allows you to, the generative model that allows you to draw samples from the previous tasks. And if we plot them, we can see, for instance, in the right part of this figure, that the episodic memory, the cross, always outperforms the generative memory. And in some cases, for instance, on CVPR10, to get the same accuracy of the generative memory, you need a buffer that is so close that, for instance, is 1.5 megabytes as compared to the generator, which is 32 megabytes. So for now, the episode, I see no point in using generative memories. However, I expect this gap to shrink as new generative models are available, and yeah, the visual quality of the images generated improves. I have to claim that the generative memory, in our experience, visual quality is not a good proxy for a good replay. So we ended up having a model that was not doing great in terms of visual quality, but was better for the replay purposes. And this thing, I think it's poorly understood, and because I would expect that better samples would yield a better replay, but that was not the case in my experience. All right, so the final slide about my model is just a visualization of the how the gates behave, really. So what you see here are two different layers, on the left for the MNIST model, on the right for the ImageNet 50 model. And we represent on the x-axis different kernels, and on the y-axis different tasks. And the color of the cell is the probability of firing of that kernel over that task. For instance, this one is the probability of firing of the 11th kernel in the task 0. And yeah, that holds for other cells as well. So we can draw some insights. So the first one is that there is some degree of kernel reuse between tasks. So for instance, here there's a cluster of kernels that are used by task 1, 2, 3, and 4. So this is good because we know that in this case, we learned that information in task 1, but we are reusing it in task 2. So we have a kind of a forward transfer of information. The second information is that we have a purple area on the right, meaning that there's still capacity here for incorporating new tasks. So these kernels are available, are never used by any task. So this model is still capable of learning. And 3, some kernels, and I want to highlight some kernels, are interpretable. For instance, if we look at this specific kernel, it fires for big strokes, regardless of the task, and it doesn't fire for thin digits. And in the ImageNet 50 models, we found kernels that fire for different tasks, but they are semantically coherent, such as different species of fishes, different breeds of dogs, different birds and penguins, some visually coherentness, I would say, coherency. And yeah, not all gates are interpretable, but some of them are. So of course, we represented the ones that they are interpretable. Some others are just not. All right, so I will discuss some limitations now. So the implementation on device can be hard because you need binary gates that are equivalent to if-else statements. So for now, gating means means multiplication by 0, basically, of the channels. And that allows you to compute the theoretical MAC count. But if you want to implement this really, you need binary gates on device, which is not something straightforward. And as a consequence of that, training becomes, again, as for other replay methods, slow, even if you have few tasks. And this depends on the backbone that you have. But for ResNet 18, which is our biggest backbone, but it's also a quite small network, I would say, it becomes quite slow. And the last one, it's not really a limitation, it's more than a trait. So the task classifier, I suspect, is susceptible to the degree of separation among tasks, meaning that if you train the same overall problem, cat versus dog versus car versus truck, the way those classes are arranged into tasks is not invariant for our model. So there may be some groupings, such as task 1 is cat dog, so animals, and task 2 is car truck, so vehicles, that are easier for the task classifier to distinguish between the same classes but different groupings, such as task 1 is cat and car and task 2 is dog and truck. I want to highlight that yeah, the assignment in our experiment, the assignment is always random, so we're more keen towards the second example, but we expect that if we build some semantically coherent tasks, the performance of the task classifier and of course of the model in turn will become better.
A question, sorry about interrupting, but this is important for us also from the audience and from me.
Sure.
When you're saying training can become very slow, how slow? What hardware did you use? How long did it take?
So for CIFAR 10 and ImageNet 50, we used ResNet 18 as a backbone. For other datasets, we used a 3-layer neural net, and it wasn't slow.
And so the hardware?
The hardware we trained on a single GPU. But they're small tasks, right? So it shouldn't be bad. I think several hours for like 6 to 7 hours for the final task on CIFAR 10 or on ImageNet 50. So the first task is typically very fast. But then the fifth task, which is our final task, it took like 6 to 10 hours. It was 1 year ago, I don't remember correctly, but that's the order of magnitude on a single GPU. And I don't remember the GPU model, I'm sorry.
Was it like high-end, really high-end, or something standard?
I think it was high-end GPU. Mm-hmm. But for a workstation, it wasn't, it was a workstation GPU, but a good one. Mm-hmm. And the reason for that also, I forgot to mention, is that sparsification of the weights has to be gentle and requires many epochs to do that. Because if you just turn off all the gates, the network doesn't learn anything. It has to be polite in turning off gates.
And if we're already in questions, so there was an interesting one from the audience about the task number and the depths of the kernels. So do you see any correlation between the task number and the depth of the kernels that are activated in the neural network?
What you mean exactly by depth of the...
So I think that the meaning is if there are more tasks, are deeper down kernels in the network get marked more as important ones for activation?
That doesn't happen because if we go back to our sparsity objective, let me just briefly, yeah. So this sparsity objective tries to weight sparsity so that the sparsification happens evenly in different layers. So there we have this bias in the loss function that prevents that, because if you don't do that, you have you have exactly what the question was mentioning. So you have that early layers are typically very active, and then as you go, and they saturate very quickly, and then as you go over and over, you have sparser patterns. But just by normalizing it, this gives the same importance to the, I mean, this balances it out. So we had to do that.
Mm-hmm. Thank you.
Yeah, I'm finished. I was just the conclusion slides. So we proposed channel gating to highlight relevant features for each task. We extended parameter isolation models with a task classifier to deal with class incremental settings. And we showed results in 4 continual learning benchmarks. And as a byproduct of the fact that we are input dependent, we can also save some computation. I just want to leave you with some future directions that I think it's interesting. So the first one, we already talked about it. So we cannot get rid of memory buffers. So this is my personal opinion. So the next question in continual learning, I think, how do we build better buffers out of the online stream? So how do we select examples to be stored? And there are some references that I put here that try to do that. The second is about general continual learning. General continual learning is this keyword that identifies continual learning with fewer assumptions during training. So we relaxed an assumption during test from task incremental to class incremental. But for instance, our model still needs task boundaries during training because you have to instantiate a new gating module, instantiate a new head for architect. You have to do some stuff at the end of the task when the task shifts from task 1 to task 2, let's say. But this you may not have that information in practice, and this also may happen gradually. So there should be a gradual shift in the distribution from a task to the next one. And this is what something that general continual learning papers are trying to tackle. And the last one, I just read this paper very recently. It tries to scale up continual learning to real world data sets. So this is about natural language processing. They collected a huge data set out of Twitter, collected in 6 years. And then you have to train a language model into, sequentially for those 6 years. And that has to, adapt to trends, and it's quite a good one, and I think it's very interesting. So yeah, thank you for listening. That took longer than I expected, but yeah, we made it, and I'm available if you have some further questions.
So anybody who has, please take this chance and raise a question. You can use your audio to ask. I will look at my questions in the meantime. So if nobody asks, I have a question I love to ask in these situations. While you were doing your research, experimenting, what unexpected challenges or difficulties did you encounter, and how were you able to solve them?
This research project has been very challenging on so many aspects, and I think that the main one was an ideological position on my side of not to use buffers. So I didn't want my model to rely on buffer because I thought that it was less elegant, right? But when the experiments, you should be pragmatic while doing your research. So if everything points you in the direction that, for instance, in our case, this single head classifier was forgetting everything, in that case, you have to listen to your experiments, and you have really to adapt to them, because it doesn't make sense to stick to your own ideological position, I think. So the way to solve this challenge was to, realize that we want to solve the problem, and in this case, the solution was to do that. Another thing, which is kind of the same, as I mentioned, we try to make this decision at a layer, at every specific layer at its own belief about the task, but that didn't work, and so we decided, all right, let's try to move everything. I mean, ease the task a little bit, and then we will recover from it. But in the end, we stick to that. So just making the problem easier and easier and easier, and then try to remove layers afterwards.
You basically regularized your own research process.
Yeah, I learned a lot, I think, in this project. This project.
I wanted to ask about the first thing you mentioned, that you didn't want to use buffers. Was this also the motivation to use the generative method? So you said, okay, I don't want to keep the buffers, but I'm okay with creating, and let's see what happens, and then it evolved from there, or it's not connected?
Really, there are just these two strategies. So when I was finalizing the work for writing a research paper, I said I will experiment with both of them, so that I will cover, most of the alternatives. I think that the reason why I did this experiment is it comes from the fact that I accepted to be more pragmatic. And what I want to say with this is that you shouldn't use in your research generative memories just because that allows you not to store examples, which feels wrong, because at least for now, at least in my experience, the experiment is telling that you should use real examples rather than generative memory. So it's just. But I chose to experiment with both of them because I knew very little about generative memories, and I wasn't sure which one would be better. And there is also this, sometimes you read in papers that that generative models, they are used for replay because for some application you may have privacy issues of storing data. But I think that most people research in this direction because it feels better than using real examples. At least it did for me.
I can give an example from the texture analysis. I read a couple of very interesting researches there. And the problem in this field is the data sets are small. Images of textures and their mathematical representation that shows the light reflections, they don't have a lot. So they have a data set problem. So what they do is they train the network with the small data set, then they use the network to recreate the texture maps, and they create more textures using that, and then they have a bigger data set, and then they do this process several times.
All right.
Until they have a big data set and a goodly trained network, which works actually very well there.
All right.
Yeah.
But I think that for textures, I can see that working. I don't know if you train iteratively a generative model on natural images, what will happen. I don't know enough about generative models. I just use them as a tool here.
Yeah, that's a very elegant way to do the entire research process on your end. I think we covered most of the important questions I have. If anybody has a question, it's a good time. Otherwise, we will close the lecture. I will have some ending words.
And if you have some, I can also take them offline. I mean.
Yeah, also on the Reddit post, you could post more questions and then we could have a discussion around them. And which is a good time for me. Last time I'm going to post all the links where you can find the community. This lecture will be recorded and posted on YouTube. It will be published on Reddit and on the Discord and on the newsletter. So you can register wherever you feel comfortable and you will have the information. How is the right way, by the way, to spell your name? Is this Davide? Because
anyway it works. I mean,
so I'm going with the
Davide.
Hebrew. I'm going with the Hebrew version, which is David.
Okay. In Italian, it's Davide with
Uh-huh.
the accent on the first. I guess, yeah, Davide. Yeah.
Okay.
The first vowel. But yeah. Anyway, it works.
So Davide, really, thank you for having this talk, for giving us of your knowledge and your experience. We appreciate it a lot. And thank you, everybody. Really, we're actually past 1,000 people now in a few months, and this is really amazing every time for me to see that the teachers and the lecturers and people who are working on really important things, they come and tell us from their craft, and to have the participation of the audience online and offline. So thank you, everybody, for joining in. And I think this is it.
Thank you. I hope it was useful, and thank you for inviting me.
Thank you. So I will wait a couple of seconds because when I close, it closes for everybody, but feel free to close off, people.
All right.
Bye-bye.
Cheers.
Thank you very much. Very interesting.
Thank you. Cheers.
Thank you very much.
Thank you very much.
Bye-bye.